Okay, good afternoon, everyone. Welcome to the fifth week of this NPTEL course on applied optics. As all of you would be familiar by now, the aim of these live sessions is to solve previous year's assignment questions so that they help you gain some problem solving experience so that you can solve the current year's assignment problems with ease. So we have completed 4 weeks, that is 1 month. 1/3 of the course is over. We are now left with 2 more months or 8 weeks to go. And this is the fifth week. So in this week, we have discussed basically interference experiments based on division of amplitude. The previous week, we had focused on interference experiments based on division of wavefront. So there are two categories of interference experiments: division of amplitude and division of wavefront. So so this week focuses on division of amplitude. Before proceeding, as always, let me just share the important links with you. So this is the link to the YouTube channel where you will find all these live problem solving sessions. The videos are available as well as they are live streamed. So if you happen to miss any of these sessions, no worries. You can go to that YouTube channel and watch the session that you missed. And also sometimes some people face some issues while logging into Zoom, and Zoom does some funny things with the bandwidth and the clarity of the video, but YouTube, the video appears perfectly fine. So if you face either some network issues or if you miss some class, then you may consider going to the YouTube channel and watching it. Okay, so now we can get started with week 5 assignment problems. So the first question, a very simple question. Hello, so am I not audible? Hello, let me just check. Hello, can you hear me? Could someone just confirm if I'm audible now? So Aarti, can you hear me now? Hello. Uh, I'm not sure if my audio has been fixed or not. So Aarti, can you hear me? Yes or no? Could you just type again? Are others also not able to hear me? Let me check in the YouTube live stream. Hello. Are others also not able to hear me? So it seems that on YouTube the audio is fine. Meaning if it is fine on YouTube, it must be fine here as well. So Aarti, you may try reconnecting your audio if that works for you. Else, you can go to this YouTube channel if you are facing some issues and watch the video over there. So I hope that resolves the issue. Okay, so let us start with the questions. Which one of the following interferometers does not work on interference by division of amplitude? So this week we have been focusing on division of amplitude. So the question is, which of these interference experiments is not based on division of amplitude? So I will start the poll. So all of you please answer in the poll. Please notice the question is, which does not work on interference by division of amplitude? I see some of you have still not answered the poll. Please answer the poll. Still there are like a few students who have not attempted the poll. Okay, let me stop the poll now. Two students have still not answered. I don't know who. So if you could please answer the poll, it is good for you. See, if you are joining the class, you should try and participate as much as possible in the class. That is the whole purpose of this live session. Okay, so I see someone is joining now. So yeah, so for all of those students who have joined now, we have just started with the first question. This week, the focus was on interference by division of amplitude. So the questions are related to that. So the first question for those students who joined just now is, which of the following interferometers does not work on interference by division of amplitude? So please answer in the poll. It is running. I will keep it open for a few more seconds for those who joined late. Okay, so I will stop the poll now. And let me share the results. So sadly, none of you have got this question right. The correct answer is, let me write down. The correct answer is option A, Young's double slit experiment. So Young's double slit experiment is based on the principle of interference by division of wave front. So we have discussed Young's double slit experiment in the previous weeks, and that was the effect of interference by division of wavefront and not division of amplitude. The Please note that the question asked which one does not work on interference by division of amplitude. It is important to note this word not that is in there. I think some of you just missed out on this word not. So you people have selected options B and C, which is Michelson interferometer and Newton's ring. All of these are examples of division of amplitude. Okay, so let me draw it for you. I thought this would be a simple question, but turns out not really. So I don't have some space. Okay, let me draw it over here. So let us see what Young's double slit experiment. Let us revise the concept of Young's double slit experiment. It seems that people have forgotten the previous concepts. So let us revise it. So what do we have in Young's double slit experiment? As the name suggests, we have a double slit. So let me draw. This is the first slit. This is the second slit. Okay. And we have a source somewhere over here. And this source is emitting light. And these are the wave fronts. So you can see that only the part of the wavefront which is between these slits will get transmitted to the right side of the double slit. So only this part of the wavefront. So that is what you are dividing the wavefront into two wavefronts. Now these will emit secondary waves like this. So you are dividing your wavefront. So that's why it is division by wavefront. This wavefront is there. These are the wavefronts. So you are dividing your incoming wavefront into two parts, and then those parts are interfering. So these wavefronts will interfere. If I draw like full like this, so these will interfere like at these are the interference. So this is what is happening. So since we are revising it, let us revise the position of constructive and destructive maxima and minima respectively. So let's say these are the rays coming, and this is from the center. These rays will meet at a screen which is placed at infinity. This is the screen, and let us say that this angle from the horizontal is theta. Okay, and we need to find out the path difference. So we will drop a perpendicular from here. So let me get rid of these wavefronts now. I think it is clear that this is division by wavefront. So I can remove these wavefront lines. They are just causing a lot of clutter. Okay, better. So this is 90 degrees. This is 90 degrees. This will also be 90 degrees. And this angle also will turn out to be theta. Why? Because if you draw a parallel line over here, so this is also theta. So this angle will be 90 degrees minus theta. And since this is 90 degrees and this is 90 minus theta, so this angle over here will be theta. Because angle on a straight line needs to be, sum total of all angles on a straight line need to be 180 degrees. So that's why this angle is theta. And this is my path difference between the two rays. And this, if let's say if this is my distance between the slits, the distance between the slits is d. Then this thing is d sine theta. So your path difference is d sine theta. So for constructive interference, what is the condition? For constructive interference, path difference should be integral multiple of wavelength. So d sine theta equals m lambda. And for destructive, you need an extra lambda by 2. So this is m plus half lambda. This is the condition for constructive and destructive interference. So I hope this revises the Young's double slit experiment, and please note that this is interference by division of wavefront and not division of amplitude. So I hope this is clear. So important thing is all of you should please read the question and what it is asking. And please do watch the videos. The videos will definitely help you in understanding the concepts and answering the questions correctly. Okay, so let us proceed to the next question. A monochromatic wave is incident on a transparent thin film. It splits into reflected and transmitted light, generally of option A. Okay, wait, this something is, yeah, this bracket is missing. Yeah, option A, same frequency and same amplitude. B, same frequency and different amplitude. C, different frequency and same amplitude. Or D, different frequency and different amplitude. So I will relaunch the poll. So please select the correct answer. Still, a lot of you are not attempting the poll. Please attempt the poll, all of you. I have kept the poll open for a longer duration of time so that all of you get the chance to attempt. Okay, I will stop the poll now. So most of you got this one right. The correct option is same frequency and different amplitude. So same frequency, because frequency is a property of the source. Once your source is decided and fixed, the frequency cannot be changed. You can change the wavelength by changing the refractive index of the medium. And so you can also change the velocity by changing the refractive index of the medium. But frequency cannot be changed. So frequency will always remain same once your source is fixed. And different amplitude will be there because of different reflection and transmission coefficients. So this is due to reflection and transmission coefficients. So let me write down again. I don't have much space here. Let me go to a new page. Okay, so this one was for question 1. Now for question 2, we are discussing the transmission and reflection coefficients. Okay, so let us say we have an interface. This is medium 1, this is medium 2. So here refractive index is N1, here it is N2. And let us consider normal incidence. So incident light is coming like this. This is incident. E0 amplitude. Then let us say reflected this is reflected amplitude ER, and this is transmitted amplitude ET. Okay, so what we have is these coefficients you can find out by using Maxwell's equation and applying boundary conditions to the interface. I will just write down the expressions for you. This is the amplitude for the reflected beam. You see how they depend on the refractive indices of the medium. And the reflectance is given by this ratio, intensity of the reflected beam over the intensity of the incident beam. And intensity is given as follows: half epsilon V E0 squared. Epsilon is the permittivity and V is the velocity. So this is velocity and this is permittivity. So this ratio will come out to be simply ER over E0 squared. So this is N1 minus N2 over N1 plus N2 whole squared. Similarly, transmittivity is the ratio of transmitted intensity to the incident intensity. And note that this time the expression will look slightly different because of the different permittivity and velocity, because the media are different for the incidence and the transmitted ray. This is what it comes out to be. And I'm using this book for the reference for all of these. This is the book. This is Introduction to Electrodynamics by DJ Griffiths. I have the third edition for this book, and later editions have also come out. So this is one of the standard introductory texts on electrodynamics. So this is the book that I'm using, and in this book, if you go to chapter 9, you will see these terms and the derivation for each of these terms you will see over there. So from there only I'm writing these things down. And from some few more important relations are that V is C over N, which is 1 over square root epsilon mu. So this is how the velocity is related to the refractive index. Okay, so and one important thing, you note that if you do R plus T, you get 1, which it should be based on conservation of energy. So energy of the incident beam or intensity of the incident beam would be sum total of the reflected beam plus the transmitted beam. And that is, it comes out this from that conservation of energy you get. So if 50% of the beam is reflected, then 50% is transmitted. If 60% of the beam is reflected, then 40% is transmitted. So this is R plus T equal to 1. That is what this relation means. And this comes from, this is consistent with the conservation of energy. But this was for normal incidents. Now we can look at oblique incidents. So again, we will have the interface. This is medium 1, this is medium 2, this is the refractive index N1, N2. But this time we have oblique incidence. So something like this. This is the normal. It makes angle theta I. Then we have reflected, which goes at the same angle theta I, because incident and reflected angles are the same. Then you have this transmitted, which is at angle theta t. So in this case, your amplitude, reflected and transmitted amplitudes are given as follows, where alpha is cos theta I over cos theta, cos theta t over cos theta I. This is alpha, and beta is mu1 n2 over mu2 n1. Mu is permeability. This is permeability. Again, we can write down the intensities. So in this case, Since it is incident at some angle, we look at the normal component. So as a result of that, the intensity is there is this cos theta term because we look at the normal component. So let us write down then. The reflectance is reflected intensity over incident intensity. Which comes out to be this. Transmittivity is transmitted intensity over incident intensity, and the expressions would be slightly different looking. This is what it comes out to be, and again r plus t is equal to 1. And as I mentioned, this is from the following book. Let me write down the reference. This is by D.J. Griffiths. And the chapter 9 of this book we need to look at. So once again, this is the book, and let me open chapter 9 for you. Yeah, chapter 9, section 3. You see here they have all the expressions and how the stuff is derived. You can check it out. Okay, so this was just to show you what the different amplitudes are. So you see that the reflected and transmitted amplitudes, they are different, and they are different from the incident amplitude, and they depend on the refractive indices of the medium that separates the interface. So if you know the refractive indices, then you know what is the reflected and transmitted amplitudes. So this was all about this question. Let us now see the next question. Soap bubbles look colorful because of A. Diffraction of light, B. Interference of light, C. Scattering of light, or D. None of these. I will relaunch the poll again. Okay, so I'm glad that all of you have attempted the poll. This is the first time that all of you are participating in the poll. Otherwise, typically I've seen that some of you do not uh, participate in the poll. So I will stop and I will share the results. So the good thing is that all of you have attempted the poll, which means all of you are paying attention. But the sad thing is that none of you have got the answer right. So I'm waiting for that day when everyone gets the answer right. But it seems today is not that day. At least this question is not that question. So the correct answer is, oh, let me change the color of my pen. The correct answer is interference of light. And this is happening based on the concept that you have learned in the very first lecture of this week, which is thin film interference. Now, soap bubbles are very thin. So, soap bubbles are very thin. They are very thin. And when I mean thin, thin means of the order of the wavelength of light. So, thin means of the order of wavelength of light. Now, they appear colorful because the thickness of the soap bubble is not uniform. It's not uniform thickness all throughout. So wherever the thickness is such that it provides you constructive interference for the violet wavelength, then you will see violet color. If the thickness is such that it corresponds to constructive interference for the red wavelength, then you will see red color. So based on the small variations in the thickness in the soap bubble, you will see the variety of colors, violet up until red. And they will be randomized, means they will not be in some uniform order, because the thickness of the soap bubble is not of uniform thickness and it does not vary in a uniform manner either. So as a result of that, somewhere you will see violet, somewhere green, somewhere red, somewhere yellow, and all over your soap bubble will look colorful. So this is because of interference of light, and in particular thin film interference. Okay, so we can proceed further. The next question is actually about the details of this thin film interference. So this was a question that introduced you one phenomenon where you really see this thin film interference in your real life, in your daily life. And this question will actually talk about the details and the mathematical identities involved for this thin film interference. So let me read out this question. Optical path difference between two first reflected wave from a dielectric thin film depends upon A. Refractive index of the thin film, B. Thickness of the thin film, C. Angle of the transmission, or D. All of these. All of these. Yeah. So I will start the poll again. Yeah. So please answer. This is based on thin film interference. What the question means when it says two first reflected waves, it means the first reflection from the top surface of the film and the second reflection from the bottom surface of the film. And we are neglecting all kinds of subsequent reflections and subsequent total internal reflections, because as you keep on reflecting the beam, the amplitude of it will keep on decreasing, as we just saw. Means the amplitude of the reflected beam goes like so. So upon subsequent reflections, the amplitude will keep on decreasing. So we neglect all reflections beyond the first two reflections. First one from the top surface, second one from the bottom surface. Okay, so let me stop the poll. Okay, again, the good thing is that all of you have attempted the poll. The correct answer, which quite a few of you got right, is all of these. And let me discuss it. Why? Let me draw it for you. So let me draw the thin film. So this is the thin film, this is the top surface, this is the bottom surface, and this refractive index is N. So I have one incident beam. Incident at an angle theta. Then the first reflection is from the top surface, like this. Okay, then there is transmission. Then reflection from the second interface is there, like this. And then finally it comes out. So we are looking at these waves. So this is the first point of reflection. This is the second point of reflection. So this angle, if we draw the normal, this angle is the incident angle theta I. This is the transmitted angle theta T. And if we draw normal here as well, then this is also theta T. And if I drop a perpendicular from here, this is perpendicular, then by geometry you can see that this angle is theta I again. Why? Because this angle is theta I, this reflected angle is also theta I. So this angle will also be theta I, and because this is normal, so it is at 90 degrees, this is 90 degrees, so this angle will be 90 minus theta I. This was also normal at 90, so that's why this angle is theta I. By simple geometry one can see. And this thickness is D, thickness of the thin film that we have. So let us label these points. Let's say if this first reflection point is A, second reflection point is B, this transmission point is C, and this normal where it is following, where it is falling on the first beam is D. So now my geometrical path difference between the two rays meaning purple ray and the pink ray, the geometric path difference is AB plus BC minus AD, because beyond the point C and D, the waves are in phase. They are parallel and they are in phase. And up until point A, since it was just the incident beam, they were again in phase. So the only phase difference that is coming, or the path difference that is coming, is AB plus BC for the pink ray and AD for the purple ray. So the difference would be AB plus BC minus AD. The optical path difference would then be N, which is refractive index, times AB plus AC, AB plus BC, sorry, minus AD, given that this medium is air. Okay, so this is air and this is some refractive index N. So optical path difference would then be N times 2AB, because AB and BC are the same. So N times 2AB minus AD. Now this is 2N. AB is what? AB is basically D by cos theta. Why? Because cos theta T, if I see here, from here I can see cos theta T is nothing but it's D over AB. So AB is D over cos theta T. So D over cos theta T minus AD. Now we can put for AD also. AD is AC sin theta I. From this triangle over here, we see AC sin theta I. So sin theta I is basically AD over AC. Okay, from here we see from here that sin theta I equals AD over AC. So AD is basically AC sin theta I. That is what we have put over here. So let us simplify further. Now what is AC? AC is nothing but 2D tan theta I. And sin theta I from Snell's law is N sin theta T. So from here to here we go by Snell's law. Snell's law states that Ni sin theta I equals N T sin theta T. Now we have taken incident medium as air. So we get sin theta I, and this transmitted medium is N sin theta T. So that's what we replace sin theta I by N sin theta T. And AC we replace by 2D tan theta I. And how we get that? Sorry, not tan theta I, it is 2D tan theta T. Sorry about that, 2D tan theta T. And how we get that? We get that from here. So what is tan theta T? Tan theta T is basically AC by 2 over D. So this gives you AC is 2D tan theta T. So let us simplify further. So optical path difference is equal to 2ND over cos theta T minus 2ND sin squared theta T over cos theta t, because tan theta is sin theta by cos theta. So this is 2nd over cos theta t is common. 1 minus sine squared theta t. So 1 minus sine squared theta is nothing but cos squared theta t. 1 minus sine squared is cos squared theta t. So this cancels. This gives you 2nd cos theta t. This is the optical path difference. Now mind you that at this point, let me highlight in green. At this point, there is rarer to denser medium, rare to dense phase, or equivalently a path shift of lambda by 2. So incorporating that, you get optical path difference would then be 2nd cos theta t plus or minus lambda by 2. The sign does not matter. It can be plus lambda by 2 or minus lambda by 2. So this is your optical path difference. And as you can see, it depends on your refractive index, your thickness, as well as the transmitted angle of transmission. And angle of transmission theta t will in turn depend on angle of incidence theta I from your Snell's law. So all these three parameters, refractive index of the thin film, thickness of the thin film, and angle of transmission, will play a role in determining what your optical path difference is. So that's why the correct option is all of these. So I hope this clarifies. Does anyone have any question up until now? If you have some question, please put in the chat box. Let me check the chat box. Okay, I don't see any comment or question in the chat box, which means people are either following everything or they are following nothing. So anyway, let us proceed to the next question. Fringes of equal thickness appear in A. Newton's ring experiment, B. Young's experiment, C. Fresnel's biprism experiment, or D. None of these. Again, the poll will be activated for all of you. All of you, please attempt the poll. I will proceed only when you all attempt it. I see that one student has still not answered. Okay, so let me stop the poll. So most of you got this one right, and I am very happy. The correct option is A, Newton's ring experiment. So fringes of equal thickness, uh, this thing comes up in the case of division of amplitude. And Newton's ring is an experiment based on interference effect based on division of amplitude. Whereas Young's experiment and Fresnel's biprism experiment, these are interference effects based on division of wave front. Okay, so we just saw the case for Young's double slit experiment over here, how it is division of wave front. The Fresnel's biprism also, Fresnel's biprism is also division of wavefront. So what happens in Fresnel's biprism? Let me draw it for you. So in Fresnel's biprism, we have a source and we have a narrow angle prism like this. When I say narrow angle, means this angle alpha is very small, and you have this source S, and what happens is the wavefronts come out. So the ray and the ray is always normal to the wavefront. So if these are the wavefronts, then these are going to be the rays. So these rays come, and due to this refraction, because of the wave of the prism, it appears as if the rays are coming from some virtual sources. These wavefronts are coming and refraction, and it appears that the rays are coming from some virtual sources, S1 and S2. So these wavefronts, they again, because of this transmission, they get split up. So it seems as if the wavefronts are being emitted from these sources. And so when these wavefronts are there, these wavefronts, they will interfere, and so it is an interference effect of a division of wavefront. And similarly, Young's experiment, we saw how it was division of wavefront, and Newton's ring is division of amplitude, and it is fringes of equal thickness. We will discuss this fringes of equal thickness in the next question, which is also based upon this fringes of equal thickness. So before that, since we have solved 5 questions, we are halfway through. Does anyone have any question up until this point? Since 5 questions are over, we can take some break. If you have some questions, please let me know. Okay, it seems like there are no questions. Let me check the YouTube chat box once. There are no questions, so we can proceed. That means. Next questions. Fizeau fringes appear when thickness of the thin film is A. Uniform, B. Non-uniform, C. Uniform but half of the incident wavelength, or D. None of these. So let me start the poll once again. Okay, so let me stop the poll now. So all of you have selected all different kinds of options. So the correct option is option B. Oh, let me change the color of my pen. Correct option is non-uniform. Sorry, there was some technical glitch happening. Yeah, now I think everything is looking fine. Okay, yeah. So the correct answer for physia of fringes appears when thickness of the thin film is non-uniform. So let us discuss this. What do we mean by physia of fringes? So physia of fringes are basically fringes of equal thickness. Okay, so this means that we obtain circular ring fringes. So ring is formed for a particular value of thickness. Okay, and this is the examples are wedge film and Newton's rings. So let me draw it for you. So wedge film means it's a wedge like this, and this is the film between these two surfaces. That's the film. And what happens is you have the rays coming from here and or maybe from here. So there are different thicknesses here, thickness T1, here thickness T2. So the thickness is different. Okay, and the other Newton's ring is, so this convex lens is there. I'm just drawing half of part of that convex lens, and then you have a flat surface beneath that. So this is the film, and again you see varying non-uniform thickness. So if I have a ray from here or a ray from here, then again you see different thicknesses. Here some thickness T1, here some thickness T2. The other type of fringes are known as Heidinger fringes. So in Heidinger fringes, what happens is these are fringes of equal inclination. This means that ring is formed for a particular inclination angle. And this happens for a uniform thin film. So we just saw uniform thin film in question number 4. So that is an example for Heidinger fringes and how you will obtain that. So let me draw. This is the uniform film. That's the film between these two surfaces. So you will have one ray which comes in and gets reflected at one particular angle, and then the transmitted will go and come, and that's how it will come for one particular angle. This is one angle. The other angle, you will see another fringe. So let's say for this angle, that's how the ray will go. Then it gets transmitted like this and like this. So this is for this is theta 1, this is theta 2. For each of these inclination angles, you will see basically different fringes based on the conditions. Okay, so let us move ahead. Next question. If the path taken by all of the interfering waves differ by the coherence length, then options are strong interference is observed, weak interference is observed, interference does not take place, or none of these. Again, the board will be active for you for a few minutes. Please answer. So the poll is active. Please attempt the poll for question 7. Yeah, hi Parnika, do you have some question? Hello. So Parnika, I see that you are on unmute. So do you have a question? And since you joined late, let me share with you the link of the important link for this course. That's the link of the YouTube channel. Hello. Yeah, hi Parnika. I can't hear you. Can you type your query if you have in the chat box? Hello. Parnika, do you mind typing in the chat box whatever query you have? In the meantime, we can discuss the answer to this 7th question. So the correct answer to the 7th question is option B. Weak interference is observed. And what happens is, for interference, for strong interference, your path difference should be less than the coherence length. Under this condition, you observe strong interference uh, fringes. And if this condition is not met, then you do not really see interference fringes. Okay, so we can proceed further to the next question. This is question number 8, again on Newton's ring experiment. And we have discussed this many times over, so I believe all of you should understand and answer this question properly. So Newton's ring experiments rely on interference by division of amplitude, interference by division of wavefront, interference by division of frequency, or none of these. So I will relaunch the poll. Please attempt the poll. So please attempt the poll. It will be beneficial for you. Also, I see someone by the name PHY. Could you please rename yourself to your name? Okay, so let me end the poll. The correct option is option A, division of amplitude. And why so? Let me draw it for you. So we have this part of the convex lens, then we have the flat surface. So what happens is, I have a ray which comes. So ray is coming and it gets reflected by the top surface and goes there. And the ray which is coming, it can, instead of getting reflected, it can get transmitted, hits the bottom surface and then gets reflected from the bottom surface. So what is happening is, we are observing reflection from the top surface and from the bottom surface. And because of this reflection at the two interfaces, we see interference by division of amplitude. Okay, because the ray is coming and it gets divided in amplitude by the reflection and transmission coefficients we just discussed over here. So these are the reflection and transmission coefficients. So the ray which is incident, part of it will get which will get reflected in the form of this purple ray. So purple ray is the reflected part, and the pink ray is the transmitted part. And they will have different amplitudes based on this reflection and transmission coefficients over here for this normal incidence case. And because they have different parts getting reflected and transmitted, this is interference by division of amplitude. Okay, so two more questions to go. This next question is on the details of Newton's ring experiments, and we will discuss the expressions involved in understanding the Newton's ring experiment. So the question is, radius of the concentric rings in the Newton's ring experiment depends upon A, radius of curvature of convex lens, B, wavelength of light used, C, refractive index of the enclosed film, or D, all of these. So I will relaunch the poll. So that's the poll. Please attempt the poll. Then we will discuss the answer. Please attempt the poll. So you have about a minute more for the poll, after which I will stop the poll. Okay, so I will stop the poll now and discuss the answer. So let me first draw the setup for Newton's ring experiment. So in Newton's ring experiment, we have a beam splitter or a partially silvered mirror. Then there is a source and light is incident. Then you have a convex lens, and there is one optically flat surface on which the convex lens is kept. And the ray goes through this convex lens and then comes back and then goes to the detector. So like that. And this is a very thin uh, plate. So oh, sorry about that. Yeah, so it's very thin, so I'm just ignoring the transmission and reflection inside this film, inside this beam splitting or partially silvered mirror. And then this goes to the detector. There is a detector over here. So this is the simple setup for Newton's ring experiment. And what is important is this region. This is where this is the part which causes the interference. So let us zoom into this region a little bit. So I have this convex lens and the optically flat surface. Like that. And this convex lens has some radius of curvature and some center. So this is the center and this radius of curvature would be R. And let us say we are looking at rays which are basically coming getting transmitted and reflected from this point. So this is the thickness D of the film, and this is the distance X. Let us call it X, and this is the film is there between this convex lens and this optically flat surface. This is the film. Okay, so what we are considering is that the rays are coming over here and then getting reflected over here, and coming in and getting reflected from the top surface. So this region we are looking where the thickness of the film is D. So we can use some simple geometry and write down some expressions. So from Pythagoras theorem, we have x squared is r squared minus r minus d whole squared, because this distance is r minus d. Okay, and if we open up the brackets, we get 2rd minus d squared, which can be approximated as 2rd for the case when r is much larger than d. So I can neglect this d squared term. Now, we need to write down the path difference. Before that, at this particular point, okay, let me use a different color maybe. At this particular point, what you have is a rarer to denser interface. This interface is rare to dense interface. Okay, maybe let me write down. I don't think I have much space, so let me bring it here. So this is the rare to dense interface, and because this reflection is happening at the rare to dense interface, this leads to a phase shift of pi phase shift, and pi phase shift means lambda by 2 path shift. This is happening due to the reflection which is occurring at the rare to dense interface. Now, we can write down the path difference. So, from these, from here, you see that the geometric path difference is 2 times d, because the ray which is getting reflected from the top surface is there, and the ray which is getting reflected from the bottom surface travels the thickness d in the film, first by going down and then by getting reflected and coming up. As a result, it traverses the distance in the film twice. So you have the geometric path difference as 2d. So this will give you optical path difference as 2nd because of the refractive index n of the film minus lambda by 2. This lambda by 2 is coming from this phase, from this path shift due to the reflection from rare to dense interface. Now we can write down the condition for constructive interference. So constructive interference will occur when your path difference is an integral multiple of the wavelength. So that means 2nd minus lambda by 2 is equal to m lambda. This is your condition for constructive interference. So this means if I simplify, 2nd is m plus half lambda. Now, if you combine these two, basically you substitute the value of 2d over here. So what you get is 2d is x squared. So n times x squared is m plus half. Okay, 2d is x squared by r. Yeah, so m plus half lambda. Now, if you write down what is x, then x is m plus half lambda r over n and square root of this. This is your value for n. Sorry, value for x. And this is the radius of the concentric rings in the Newton's rings, because this x is the radius from the center, and you will see uh, uh, rings of this particular radius, of x radius. Why of x radius? Because at x distance from the center, the thickness of the film remains constant. So you are from the center, if you go x distance along theta equal to 0 or theta equal to 30 or theta equal to 60 degrees, it doesn't matter, the thickness of the film will remain same throughout. As a result, the phase difference caused by that particular thickness of the film will be the same. So if the phase difference is same, the path difference will be the same, and that will correspond to one particular ring you will see. Whether it is a constructive ring or destructive ring depends on the thickness of the film. So this you can clearly see that the radius of the rings depends on the wavelength lambda, the radius of curvature of the convex lens capital R, and the refractive index of the film n. As a result, the correct option is all of these. So now we move on to the last question for this week. This is on Michelson interferometer. So the question is, in Michelson interferometer, okay, sorry, there is some technical glitch. Let me fix this. My screen is still not visible. Yeah, now I think it is visible. Yeah, sorry about that technical glitch. Now I think everything is fine. So this is the last question for week 5, and it is based on Michelson interferometer. The question is, in Michelson interferometer, if the path difference between two mirrors is decreased, then the fringe pattern will be A, remains same, B, shrink towards center, C, spread away from the center, or D, none of the above. So I will relaunch the poll one last time for this session. Please answer the poll, and then I will discuss the answer. So all of you have about 1 more minute left for attempting the poll. Okay, so let me end the poll. So the correct answer is option B, shrink towards the center. So if you decrease the path difference between the two mirrors, then fringes collapse towards the center. And when the path difference between the two mirrors is 0, then you see complete darkness. So let us discuss Michelson interferometer. So Michelson interferometer is based on the concept of division of amplitude. And let me draw the setup. So we have a beam splitter. There is a source. And we have ray coming in. And then we have a ray which gets reflected from the beam splitter. And then we have mirrors. So there's a mirror over here. There's a mirror over here. So the ray which is coming in, part of it gets transmitted, part of it gets reflected, and then from the mirrors it gets reflected back again. It arrives at the mirror, combines at the beam splitter, and then gets reflected from the beam splitter and then detected at a detector. So this is the setup, very simple setup for Michelson interferometer. And what we have in our control is we can move this mirror. We can move this mirror and this mirror can come to a new position over here. And let's say this mirror has moved by a distance d. Then your ray travels basically extra distance of 2d. D to the mirror and then d back. So your geometric path difference is 2d. And then we can draw its linear equivalent, the straight line equivalent we can draw. So let's say this is one mirror. This is, let's say, the virtual image of the mirror. And this distance is 2d. So what we have is, we have a ray coming up like this. This is the horizontal, and a ray coming from this mirror like this, and then we have a screen kept far away at infinity, which is the detector, and this angle is, let's say, theta. So if we draw a perpendicular over here, then this distance is 2d cos theta. So when you are looking at the center, then your path difference is 2d. But when you're looking at some angle from the center, then your path difference is 2d cos of theta. And the optical path difference would then be it will be 2d cos theta minus lambda by 2. Where does this lambda by 2 come from? This comes from the pi phase shift due to reflection. Now, for the case of constructive interference, we have 2d cos theta minus lambda by 2 equals m lambda. That means 2d cos theta equals m plus half lambda. And for destructive, we have 2d cos theta minus lambda by 2 equals m minus 1 by 2 lambda, which implies 2d cos theta equals m lambda. Now, if d decreases, then what will happen? Then theta also decreases such that cos theta increases so that my product, so that d cos theta product remains constant. And it will remain constant for fixed value of m and lambda, for fixed value of m and lambda. So this condition, if d increases then theta decreases, would imply that your fringes collapse in the center. And the reverse will happen. If instead of decreasing the d, if your d increases, then your theta will increase. That means fringes appear to come out or spread away from the center. So that's the question. And we can discuss some more aspects of the Michelson interferometer while we are at it. So let me draw. Let me draw a little bit zoomed in version of this beam splitter so that we can see actually what is happening. So this is a zoomed in version of the beam splitter. And let me take a color. So this is my source coming in. Source light is coming in. It gets transmitted like this into the material of the beam splitter and gets reflected from this back reflecting surface. From this is the reflecting surface. Okay, gets reflected, comes out, goes to the mirror. There is the mirror. Then, so let me draw the arrows. So this is the input source. Source goes in like this. Then goes to the mirror, gets reflected from the mirror, retraces its path like this. and then exits from the beam splitter like this and goes to the detector. There's the detector. The other path is the source is coming in. It's going through this material, but now it gets transmitted and comes out like this. Comes out, hits the mirror, gets reflected from the mirror, goes back, and then gets reflected again to come out along the same purple line like this. Okay, now at this particular point you have a rarer to denser interface. So because of this you have a pi phase shift in the pink ray. But notice that there is another thing happening over here. If you look at the purple ray, then it goes 3 times in the plate, in the medium of this beam splitter. How 3 times? It goes in here once, then gets reflected, then when it comes back from the mirror, again it traverses this path and then comes out. So 3 times in the plate. You see 3 arrows I have drawn. Whereas the pink ray goes only 1 time in the plate. So you see only 1 arrow I have drawn. So it comes, gets transmitted, and then transmitted and comes out. So as a result, there is a difference in the amount of, in the distance traversed in the plate. So we can get rid of that by using what is known as the compensator. So we will make use of a compensator. A compensator is nothing but a glass material or a material of exact same refractive index as used for the beam splitter and exact same thickness. It just doesn't have that partially silvered part. So there is no reflection happening, only transmission is happening. Okay, someone is saying pink and purple colors are not appearing very different. Okay, sorry about that. Maybe next time I'll take care of that, but you can follow the concept while I'm drawing. I will draw again and you can follow the path of the rays. So let me redraw again with the compensator. Okay, I need to select this whole thing, copy and paste it. So now I will make use of the compensator. So what the compensator is, let me add it. So compensator is just another material of same refractive index as the beam splitter and same thickness. Just it does not have that partially silvered part. So no reflection will happen, only transmission. And this time the pink ray will go here, then get refracted like this, then it goes like this, comes out. So this is the path. Then it hits the mirror. Okay, sorry, this is tilted. It hits a mirror and gets reflected back again. So it goes and it retraces its path and comes out. So now you can see that the pink ray also travels 3 times in the medium. and the purple ray is also traveling 3 times in the medium. So that path difference is compensated. That's the role of the compensator. So that is all about this Michelson interferometer, and this completes our session for week 5. See you in the next week, next session on Saturday for week 6. Okay, thank you everyone. Bye bye. Okay, so thank you, and the lecture is over and people can leave the meeting now.